Okay. All right. So I want to start by thanking the organizers, particularly Bhavani and others, for organizing this conference in this wonderful venue. This is my first visit to ICTS, but I hope it will not be the last. And I know I'm against the clock for lunch, so I'll try to keep it really brief and not go over my time. But I think that, so today, I guess the title is changed a little bit because I want to tell you about some work we have been doing, which is sort of quantum simulations of PT Hamiltonians. My general interest in the last few years has been to try and understand what is PT Hamiltonians, or more specifically, what are their physical manifestations in classical quantum settings, whether they are in optical, mechanical, electrical, whatever have you, but just basically, what do these different realizations tell you, okay? And so this particular work is done with my graduate student, Andrew Harter, who is graduating very soon, and Professor Dr. Anthony Liang, who is at University of Bristol, and his group, where the experiments were carried out, okay? And then I actually got into this area because of some high school students at Indianapolis, where we have this summer high school student program. And those have been sort of long-running collaborators in this endeavor. Okay. Now here everybody is sort of, or most of you are familiar with the PT. I see many familiar faces, but because there are some people who are new to this, I'm gonna this is the outline of my talk. I'll talk a little bit about the history of PT Hamiltonians the way I understand it. And the bottom line message is that PT traditionally has been considered a classical system with some sort of balance gain and loss, although their quantum versions are something of a question, okay? And then because there is a question regarding whether you can sort of do quantum Hamiltonians at a quantum level, which are PT symmetric, what we did was to instead sort of bypass this question and just consider simulations of such Hamiltonians by using something called unitary dilation, which allows you to actually simulate a PT quantum system or a genuine PT Hamiltonian. Now, there is, of course, a question of what is meant by quantum, whether lasers are quantum, whether many body correlations are quantum, whether you would call measurement of density matrix and entropy and quantum information pieces as quantum, okay? And so in particular, I'll show you examples of bosonic correlations evolving under a PT symmetric Hamiltonian, as well as quantum information things which evolve under a PT symmetric Hamiltonian, okay? And then I'll have conclusions. There are other examples, but I don't think I'll have time for it. And this was in 2015, where PT showed up in one of these cartoons in Nature Physics. And I guess by that, in another 3 years, it's been now, it has really exploded and in various directions. And I think quantum is one of the directions where there's still a lot of exciting room to make new things. All right. So the way I understand this PT business is something that I got into it about 2011 or something like that. But I still remember when I was a postdoc reading a paper by Carl Bender, which talked about real spectra for non-Hermitian Hamiltonians. And so, I apologize to the experts in the sort of audience, but the history is essentially that you started out by considering some continuum models which had potentials which were not Hermitian. So they looked very unphysical. For example, if epsilon is 1, this is ix cubed, which does not really make any sense. But if you calculate its spectrum as a function, so that's the energy as a function of epsilon at epsilon equals 1, you find the spectrum to be purely real. And that was sort of the bottom line. And since then, this has been generalized to typical models where you have a Hermitian kinetic energy term, so that's the baseline, and you have a non-Hermitian potential, which is invariant under combined parity and time reversal operation, or in general, a potential which is sort of symmetric under some antilinear operation, basically. And what you find is you have real spectra for small non-hermiticity, complex spectra for large non-hermiticity, and this sort of transition is what you call PT symmetry breaking. So that's just definitions, basically. And I'm sorry, what's the question? I don't know. Okay. So More specifically, if you, okay, so short answer is I indeed do not know, but the wave functions of this, if you want to calculate, it's a fairly difficult task because the wave functions don't live on a real line and you want to sort of ensure square integrability, then you have to use Stokes wedges and things like that. But because I don't understand most of that, I just deal with matrices, which are simple and for which I can do all the calculations. So even a matrix like this, which is a spin model or a single qubit, if you wish, or a two-level system, having gain and loss, well, the eigenvalues of this 2 by 2 matrix are given by that. And you can tell that these ones will be real when the non-hermiticity is small, and they will become complex conjugate pairs when the non-hermiticity is large. So, and for the rest of the talk, I'm just going to deal with matrices, Okay. All right, so if you have real eigenvalues, what's next? And traditionally, or I guess since after the first paper, the main sort of effort were to develop a self-consistent quantum theory, okay? And the cost you pay for these real eigenvalues here is that the eigenfunctions are not orthogonal, and therefore the time evolution is not unitary under the standard Dirac norm. And one of the things you could sort of think about is, well, maybe find some similarity transformation to make the Hamiltonian self-adjoint as long as the eigenvalues are real, okay? And then you can get a unitary evolution under some newly defined norm, and you have fundamental theory, you can study lots of interesting problems, you can define thermodynamics, you can do shortest time problem, and things like that. Once you have established a unitary evolution, okay, under some newly defined inner product that you use for your space, okay? Now, this approach has been sort of, a lot of mathematical physics and strong work, and it does give rise to some interesting things that I am sort of been interested in. One of them is, what are the properties of pseudo-Hermitian random matrices? Everybody's familiar with properties of sort of Hermitian random matrices. You get Wigner distribution, you get different statistics depending on whether they are complex entries or real. And if you have pseudo-Hermitian random matrices, then instead of having a Wigner distribution for level density, you might get some other different types of level densities, okay? So these are kind of things you can do, okay? The other interesting problem in this sort of an approach is to try and find what are the constants of motion. So let's say if I have a system and it's undergoing PT evolution under a PT Hamiltonian, what are the things which are conserved, basically, okay? No. So this was one of the approaches. Which is so-called sort of, consistent quantum theory or complex extension of quantum mechanics, which was sort of the title of the paper from 2001, where I first read about PT symmetry, okay? Now, the constraints of this, or the cost of this, is that this procedure is only valid in the PT symmetric region, or in other words, you say that the Hamiltonian makes sense only when it has real spectrum. When the non-hermiticity becomes very large, fundamentally, I will not consider it as a model, and because it has no meaning, I cannot do the similarity transformation to a self-adjoint one, okay? The other sort of cost is that the intertwining operator, or the metric operator, or whatever you want to call it, they depend on H in general. And therefore, the new inner product that you are using to make self-consistent quantum theory depends on H. So you change the system, and you change the definition of how you calculate observables, because inner product is how we calculate observables, okay? So in general, for example, in discrete models, that means that spin operators do not remain observables, and by that I mean they will not necessarily give you real expectation value under this new inner product, right? There are some fundamental issues as well. And so this has been one process, but through which there haven't been any experimental evidence of systems which evolved according to these sort of new inner products. It looks like nature evolves according to Dirac inner product, as far as we know. The second option which came about was from optics by Dimitris Studolides and his large group of co-workers, basically. And their observation was that, we have Schrodinger equation, but that's the same as paraxial approximation Maxwell equation when light is propagating in waveguides, okay? And so in the case of paraxial approximation in this waveguide case, though, the potential of the Schrodinger equation is replaced by what is the index of refraction in the waveguide. And that one we know how to make complex. Naturally, there is dissipation, which means we know how to have an index of refraction which is a negative imaginary part. And with some engineering, you can make it positive as well. Okay? So PT symmetry just translates into this sort of an equation, which is n star of minus x equals n of x. Or this is basically that if you have gain on this side, then I need to have a loss on its mirror symmetric side. And therefore, PT systems are nothing but just balanced gain and loss systems. That would be another way of looking at it. Okay? And this really, I think, changed or opened the floodgates of experiments. And there have been, since then, experiments in electrical circuits, in simple mechanical pendulum, because all you have is an idea of a system which has some loss, which is coupled to its time-reversed version, which is to say, which has some gain, which is spatially separated. And then you see what happens when the communication between those two systems is increased or decreased, basically, vis-a-vis whatever is the loss rate. Okay? And this led to a bunch of, a ton of experiments, basically, which all come from this idea that a PT system is fundamentally a gain-loss system. It's an open system. So I don't care about unitarity, because I'm not talking about some fundamental description of nature. I'm talking about a specific type of open system, which has gain and loss in spatially separated parts of the system. And so I will just use normal quantum mechanics formalism to do my calculations to see what happens in an experiment or to make predictions, basically. But I will not get unitarity because stuff is not conserved in this system. And that's okay. I'm not claiming it to be a fundamental theory. Okay? All right. So what then? So before I go on, I just want to sort of, remind you of what are the key properties or fundamental properties of such a PT system. Okay? And so this is the cartoon for it. What I have here is a two-side system or a two-level system where the red represents the gain side and the blue represents the loss side. And that basically is given by this Hamiltonian that I mentioned. Okay? So these two could be waveguides, which are coupled by evanescent coupling. And so J is the effective coupling between those two waveguides. Light goes back and forth between them. Gets absorbed here, gets amplified here. Okay? That's what this would mean. In the case of, let's say, Bose-Einstein condensate or some other realization, if you want, these could be two quantum wells where, these two wells where the particles go back and forth. But then this one has a leakage and this one is getting pumped, where particles show up. So effectively, the number is increasing with time. Okay? This could be electrical circuits as well, where this one is an LC oscillator, okay, which has a Joule heating, which is inductively coupled to another LC oscillator, but that one has some gain in it. Okay? So you have some op-amp and something like that, such that it's increasing the total current in it instead of decaying. Right? And so this is a prototype, but it's quite useful prototype because it turns out in the end, all you need is really two levels because the PT dynamics is driven by, two levels coming together and then becoming degenerate. And so in the end, when you are close to the critical point or close to the point where the PT transition happens, only two levels in the spectrum matter. Or in general, if it depends on the degree of the exceptional point of the transition point, but those many levels is all that will matter, not the rest of the spectrum. So prototypically, this is a good Hamiltonian. What are the properties of it? Well, I'll calculate time-evolved state. It will not have a conserved norm, fine. But the key properties of this quantity, which I'll call intensity, which is just the norm of an initial state, basically, is that when the eigenvalues are real, this quantity oscillates, okay, as a function of time. In a Hermitian quantum mechanics, this quantity would be constant with time, because that's unitary evolution. In this system, which is an open system with some gain and loss, this quantity will oscillate, and the eigenfunctions would be eigenfunctions of the PT operator. And roughly speaking, what that means is you cannot really tell which one is the gain side and which one is the loss side in the system. Basically, the behavior looks like symmetric between gain and loss. You cannot tell which one is the gain side or the loss side. Yeah.
In principle.
Which part?
This oscillation are due to the fact that you're working in a two-dimensional or in a finite dimensional Hilbert space. So when you make your computation, you just have to diagonalize an Hamiltonian, and the eigenvalues are
all real.
All real, so you have oscillation. But when you move to an infinite dimensional Hilbert space, which you are not doing here, I guess, but I suspect that something different may happen, so you have no oscillation necessarily.
That's possible. I don't know. I mean, you know, reality of the eigenvalues and completeness of the states, non-orthogonal states, if that works, then the oscillation should happen because that's how you generally expand it. But the existence of those for infinite dimensional operators, I don't understand. Okay. Yeah. All right. So in the PT symmetric phase, what that means is essentially you get oscillations or oscillatory behavior, and roughly speaking, gain and loss are not distinguishable. At the exceptional point where there is two eigenvalues are becoming degenerate, you get a power law growth for this, basically, this non-unitary evolution, fine. And then in the PT broken region, where the eigenvalues are complex, you can clearly tell the gain side, because that is where the large part of the intensities resides, or in other words, the eigenfunctions are broken, basically, or they are not simultaneous eigenfunctions of the PT operator. And this is just a cartoon showing how generically the eigenvalues of the PT operator, of this sort of Hamiltonian, change as a function of the non-Hermiticity parameter. What you get is you have two eigenvalues, they come together, and then they become degenerate, and then they flow. And that is very generic, basically. Okay? Whether it's a two-dimensional system or multi-dimensional system, it doesn't matter.
Single spin to a bath. Is it possible to connect to bath and make sure you just generate this I gamma term and nothing else?
No, or at least I am not aware of. If I have a two-level system which is acting as a single spin, basically, like a degenerate Fermi gas in its lowest to hyperfine levels, then we know how to create the loss part. We do not know, as far as I know, we do not know how to create that part.
Okay, so then how do you realize this? I mean, in the sense, if there are many ways to make two-level systems, right? And there are many ways to connect two-level systems to harmonic modes, infinite harmonic modes. So you're saying there's no way to just realize effectively this non-Hermitian Hamiltonian?
Okay, that is where the question of Hamiltonian comes into play. This has been realized in optical settings in numerous times, basically, you know. And because that is where you have bulk light and you have gain, which is easily doable. There are proposals to realize this in Bose-Einstein condensates, which are well-defined mathematically, but experimentally are very challenging because there you need a lot of reservoir engineering in terms of time-dependent amplitudes, coupling amplitudes, and things like that to get that. So there are no experiments to that. There is a recent proposal on cavity QED, as you are aware of, with Franco Nori and et al. It's in PRA, I think, last week or something like that, where also they propose that this can be generated through some engineering like that, to a bath which is not going to be thermal, but have some complicated properties. Yeah. Okay, right. So, very good. So, 16 minutes. All right. Is that the time I have left? Okay, all right. Okay, so the question is, we know how to do all of this classically. There have been numerous experiments doing this classically. But what about quantum? Now, can we do this at a quantum level? Or are we just sort of playing with words where mapping, you know, Maxwell equation into isomorphic stuff and so on? Okay. So with optics, as far as I know, it has not been done. And one of the major issues is that loss is linear down to single photon level. So if I have two waveguides and I started putting in single photons, then the loss channel will statistically still give me a result which is effectively like a minus I gamma potential. But with the gain, that is nonlinear and random. There is this spontaneous emission part, which you ignore when you are doing experiments with bulk light, basically. Because that contribution is very small, and so you ignore it, and therefore you can create balance gain and loss when you have large number of bosons which are doing this sort of effective modeling. Okay. So that one is a problem. Okay. Whether you can really simulate gain-loss Hamiltonian, or in other words, can you create a fundamentally quantum system which has a gain and a loss? It has to be Bosonic system, obviously, because you have gain. Okay? And fermions, basically the Pauli principle will exclude that. So this one is a question, because I'm not aware of an answer. And I have talked to people and have not really received any sort of, seen an answer which is satisfactory, whether you can do it. Now, there is a isomorphism between this sort of a Hamiltonian and a localized loss system as well. So in other words, instead of having a PT symmetric system, you have a system where there's no loss and loss. And that system maps in terms of exceptional point structure and so on onto a PT system. Okay? And in this case, you can actually do things at a quantum level, basically. Okay? And in fact, I guess Hideaki Obuse and Peng Zhu had a paper about this, very nice one last year, where they used loss only, selective loss on the system to sort of realize a PT Hamiltonian at a single photon level. Yes. Oh, sorry, this is continuous time quantum walk. So in other words, I'm thinking about creating a Hamiltonian. And this would be discrete time quantum walk. So the fourth one is, instead of trying to construct the Hamiltonian, can I simulate the time evolution, which is what we observe experimentally? Or in other words, can I have some sort of a discrete time quantum walk version where I am getting results or implementing results which are consistent with a PT Hamiltonian? Now, the main issue is that the time evolution operator is not unitary, and that leads to problems. The question is, how do you simulate a non-unitary operator by using quantum simulators, which are typically unitary? Or you try very hard to make them unitary, basically. Remove all sources of error, and so on and so forth. And it turns out there is a procedure for it, which was sort of, outlined by Halmos in 1940s or something. It's called unitary dilation. Okay? And the idea is that instead of, creating a new Hamiltonian, you're basically taking this time evolution operator and mapping it into some sub-block of a larger unitary, which is twice the size. The details of that I'll not really go into, because I think we don't have time. But the basic picture is the following. You start out with essentially a system. You have some non-unitary time evolution operator G that you want to simulate. You map it into a larger unitary, which is twice the size. And then you take the results just in the upper block, which is your region of interest, and then you're done, basically. Okay? The procedure for this, the procedure for this I'll explain a little bit later on Friday when I give a substitute talk for Anthony Liang, where we simulated some unitary and non-unitary dynamics in this paper, basically. But the idea is that this is a procedure which is applicable in both PT symmetric and PT broken regions, because this is a procedure you can do generally. Okay? Right? You need a 2m by 2m unitary for an m-dimensional system. I should point out this is neither the Naimark or other Hamiltonian dilations which have been discussed in the literature, where those dilations are applicable only in the PT symmetric phase where you have a real spectrum to be able to construct and do procedures. All right, so you have such a system, you measure, and so if you have an ability to create a unitary that you want, then you have the ability to simulate whatever PT symmetric Hamilton that you want. Okay, that's the bottom line. And then, if you have a system like that, you start out with, you can measure coincidences with multiple photons, you can create the full density matrix, you can obtain quantum information properties and all of that by essentially looking at what would be the time evolution for that particular PT symmetric Hamiltonian and embedding it into time evolution for a larger system. And that's basically the key idea. So here are some results. These are results for bosonic correlations, for example. So the system that we have is a 3-site PT system, which has been in optical setting created like last year with Christo Delights group, for example. So I have what is shown here. This is a picture of, that is the loss site, that is the gain site, and this is the neutral site. So I have 3 sites, okay? Right. And those colors show where I have put in 2 photons. Okay? So this would be a case where I put in 2 photons, one in the gain side, one in the loss side, one in the neutral side. Okay? And then these ones are measurements for the probability of finding them in other channels. So you put in 2 photons in these 3 channels. And then what's the probability of finding them in the same channel? That would be the blue and the black. What is the probability of finding one in the gain side, one in the loss side? That would be the another one. Or what is the probability of finding one in the neutral side, one in the gain side? That's sort of the other possibility. Those are the questions that you would ask. Okay? In each case, what is shown here is the time evolution of that joint probability as a function of gamma over j, which is basically the quantity which determines the PT threshold. Okay? So roughly speaking, in that corner is the Hermitian limit. Here is where PT breaking happens because it happens at root 2 or 1.41. Okay? Right. And all the plots are sort of, the surfaces are theory and all the points are experimental data, basically. So what you have is a chip which can do unitary operations on a 6 modes. And you can put in 2 single photons at a time or 3 single photons at a time. And this sort of benchmarks it, or to some extent says that this evolution behaves very well according to what you would expect by theoretical calculations. Now, what is of interest? In some sense, aren't we doing trivial things? One is, it's a proof of principle of how do you simulate non-Hermitian systems, and more specifically, PT symmetric systems. The second one, and more important, is that this problem, which is bosonic correlations, or more generally known as boson sampling problem, basically, is a problem which is hard or difficult, computationally hard as well, in the Hermitian limit. That is something that is known. That if you just wanted to send in, 5 bosons in 20 waveguides and wanted to predict what's the output distribution, then that problem is related to calculating permanents. And permanents, as opposed to determinants, basically are difficult, exponentially harder. So there is some interest from computer science point of view regarding what would happen to this evolution if you are now considering evolution not under Hermitian Hamiltonians, but rather under PT symmetric Hamiltonians. Now, there are other interesting properties that this picture shows. So, for example, this one is where I put in one in the loss side, one in the gain side. Okay? And I measure, one in the loss side, one in the neutral side. And I measure what happens in the loss side and the neutral side. Okay? You'll notice this picture looks awfully similar to this picture. Okay? And that is where I'm putting in one in the gain side and the neutral side, and measuring in the gain side and the neutral side. But these 2 pictures are not identical, actually. If you look at it, you'll find they are similar in the PT symmetric region, whereas in the PT broken region, which is this range where gamma over j is like 1.5, very high, these 2 differ. And that's an explicit demonstration, if you wish, of what I had mentioned earlier as key signatures of PT symmetric breaking, or PT symmetric phase and PT broken phase. In the PT symmetric phase, you find that the gain and loss are roughly interchangeable. You cannot distinguish between them because the communication between those 2 things is very high. On the other hand, if you're in the PT broken phase, you can very clearly tell which is the gain side, which is the loss side. And that is manifest here in results being different in this region where gamma over j, or the non-hermiticity, is very high. That's this curve, for example, versus this curve. On the other hand, when gamma over j is small, these parts are equal to each other, and there is a mathematical relation, actually, you can sort of, pictorially, whatever I'm showing, there is a mathematical relation you can prove that must exist in these many-body correlations that are there. Okay? You can do similar things with 3 photons, basically. This is where you put in 3 photons, one in the gain side, one in the loss, and one in the neutral side, and then measure all coincidences possible. Okay? And what you find is that the result for 2 in the loss and 1 in the neutral side, and the results for 2 in the gain and 1 in the neutral sides, they are related to each other if you are in the PT symmetric phase. Once again, you can't tell which is gain, which is loss. If you go to PT broken phase, then these results are not related to each other. Yeah. So in the experiment, the choice is made by what G you are dialing, in some sense, or what is the time evolution operator corresponding to it. So The calculation of that is what allows you to choose whether you're in the PT symmetric phase or PT broken phase. Okay. How much time I have? That plus questions or just that? Okay, we shall see. All right. No, I mean, I'm almost over. I can talk for another hour, but I don't want to. It's lunchtime. All right. So let me end by telling you about a couple of more things that we have been doing, which are regarding quantum information in this PT system. Okay. What I did earlier was just to try and show how multi-boson statistics or, multi-particle statistics behaves when you are evolving under a PT Hamiltonian. And this is genuine quantum in the sense of these are indistinguishable photons whose statistics are being measured. And if we introduce a phase difference between those photons to make it distinguishable, then we find that coincidence rates go different than what you would expect when, you have classical behavior, okay? So you see the quantum bosonic enhancement that is there in these results, basically, okay? Now I want to talk about what happens to other things. So one of the good things about this sort of approach is that because you have a full control over Unitary and you can do measurement of all the output ports, you can basically construct the entire density matrix of the measurement. And once you have the full density, quantum density matrix for the system, you are therefore able to create reduced density matrices, calculate all kinds of things that you want to calculate, entanglement entropy, mutual information, just the entropy of the system, whatever have you. Okay. And so these are some of the results that come about from that sort of a process. So this is an example of what happens to entropy of a maximally mixed state of a single qubit. So I have a two-site system or a single qubit under a PT Hamiltonian. If I have a Hermitian Hamiltonian and I start with a maximally mixed state, or any other state for that matter, the entropy doesn't change with time. We know that, basically. The question is, what happens when instead of maximally mixed state, instead of that, it's evolving under a PT Hamiltonian, okay? So these are experimental measurements from a while ago, actually. What you find is, instead of this being a flat, so what is shown here? Entropy as a function of time and as a function of non-hermiticity, going from 0, that's the Hermitian limit, to 1 here, which is the PT breaking limit, to beyond PT breaking limit. Okay? So in other words, we are accessing all phases, PT symmetric phase, PT exceptional point, PT broken phase. Okay? And what do you find? Well, when you are in the PT symmetric phase, the entropy is not constant, it becomes oscillatory. Okay? And this is something that has also been observed in a paper last year, in a theory paper last year as well, by Ueda's group with Kawabata and others, basically. And I think there was a poster regarding it at the Biohanif conference, actually, I recall. Yeah. So in this case, again, all the lines are theory, all the points are the experimental data, where you started, took a single photon, evolved it, obtained the density matrix, calculated the entropy, and seeing what happens, basically. And what you see is what you expect, again, essentially, that the entropy shows oscillatory behavior, and then it goes over to a steady state value, either algebraically or exponentially, depending on whether you are at the exceptional point or in the PT broken phase. Okay? But with this system, you can do more. So, for example, you could put in mixed states instead of a maximally mixed state that was considered here. You could put in any arbitrary initial density matrix or state of a single photon, or you can do it with 2 photons. We have done both of those things. And then you can measure how much is the entropy in one part of the system, basically, in other part of the system, what is the mutual information between them, which is related to the difference of the entropies, basically, what is the concurrence, and so on and so forth. Okay. And so these are sort of representative results, which show that if I have a state, now this one is a pictorial representation of the density matrix in the basis for this single qubit. So if I have a single qubit, my unitary dilated system has a dimension of 4, because instead of 2, it's 2 into 2, which is 4. So you are putting in some state like this, which basically says that there is, some weight in being the upspin, some weight being the down one, and some coherence between the two as well. And in each case, what you find is that for the, and the red, well, in each case, the lines are the theory, the points are the experimental data of the fully constructed density matrix and the submatrices that you get from it. And the interesting behaviors that are here are the following. One, depending on the system, you might have the total entropy to be constant, basically, or not. It's a system undergoing evolution under PT, and it depends on what you are doing. These are all results in the PT symmetric phase, which is why you are seeing oscillatory behavior that we expect, basically. Okay? The period of oscillation starts to become longer and longer as you get closer to the PT boundary. Okay. There are other interesting things that come about, and that relate to what happens to the entropies in the part of the system versus the environment that this unitary dilation model couples it to. This is a part which I did not really mention very much, but this PT system, when I talk about unitary dilation, what it turns out is it's sort of like this PT system is coupled to its time-reversed work. That is what the unitary dilation physically represents. Okay. And so you could imagine how much is the entropy in this, how much is the entropy in the environment, how much is the flow back and forth. And those are the results which are given by these pictures. Okay. So in some cases, you can see that the entropy of the environment, which is the red curve, and the entropy in the system, which is the blue curve, they go together. There are some cases where they go in opposite directions. So in other words, the entropy in the system is increasing, the entropy in the environment is decreasing. Okay. That depends on what choice of initial state that you have put in, basically. And so there's a lot to play around here to sort of fully understand how does quantum information or quantum properties evolving under a PT Hamiltonian behave. So I think with that, I'm going to finish up. I guess the main things I wanted to sort of tell you is that there's an approach called unitary dilation, which is applicable across the range of parameters. So in other words, applicable in the PT symmetric phase, exceptional point PT broken phase, which allows you to do genuine quantum simulation of PT symmetric Hamiltonians. Allows you to measure multi-particle coincidences, density matrices, coherence, and all quantum information pieces that you want to calculate. Okay. There are, of course, this one is a unitary dilation, so this is like a discrete time quantum walk approach. These questions are still there, and I'm not going to talk more about it. And the last thing that I want to tell you about is that this is all 2x2, 3x3 physics. You know, it's very simple, at least theoretically. Experimentally, it's hard. It's really hard. But theoretically, it's very simple. And so these are all the kids from my high school student research program who sort of got me into this area. You know, do simple calculations, try to see what you find, whether find something interesting. And in that sense, it's an area which has been extremely accessible to high school students. And it's one of the things which we sort of continue to do at IUPUI is basically get students involved in something really forefront in terms of research, but is still accessible to them. So I think with that, I'll stop and take any questions.
Thanks to the speaker. We had some discussions, so we have 2 minutes. So please, very, very short questions. And
what do these papers deal with? You have listed a set of papers here.
These are all papers where the primary work was done by these kids. They usually studied tight binding lattice models or tight binding hopping models with PT symmetric impurities to study when the phase transitions happen, how the observables work out, and things like that. The calculations were usually done analytically or with MATLAB when it goes to larger. But these are all papers where it's essentially students are the main authors.
So it deals with PT symmetric systems.
Yes.
The quantum systems, you know, in a different regime, of course, continuous thing. Has anybody looked at Shannon entropy and such things, and you know, in terms of integral rho ln rho kind of stuff, you know?
I don't know. No.
The last short question.
Hello. I appreciated your historical introduction because I'm from outside of this field, but I have a question about your theory, and that is what I do know is when you have loss, you also have fluctuations. So you have the fluctuation dissipation theorem, and in particular, if you have a lossy system, say a harmonic oscillator, you need to, your commutation relations between your Heisenberg operators are not preserved in time, unless you add in some fluctuation. Is that the case here? Are your commutation relations preserved? You were talking about a bosonic system and so on.
Right. So I think it's a very difficult and challenging question, what you have asked. And that is why PT has been realized only in optics, a very special kind of boson, as opposed to any other kind of optics, any other kind of bosonic realization, basically. No. So what you are saying is...
You mean classical optics as opposed to quantum optics?
Yeah.
Yeah, sure, then the commutation relations don't exist.
Yeah, no. So I think that, I mean, more fundamentally, the question is, can I have a loss with essentially zero temperature in the region such that the fluctuation part, which is the Langevin noise or whatever you want to call it, is small enough to be negligible? And on the other side, can I have a Langevin term with small enough drag coefficient, if you wish, or a deterministic, gain term rather, with a small enough loss, basically, such that I can realize a truly PT Hamiltonian. And I mean, that is one question. Actually, that is the question, and that's why.
Okay, because it is deep question, I suggest that the answer will be postponed to the couloirs.
Yeah.
Because there is a lot of things to exchange. I mean, that's why we have long breaks. So let's thank the speaker for answers again.
Yeah.